Hello. We're going to talk about some of the work that we're doing in the area of artificial intelligence, in particular on reinforcement learning and its application in power systems. These are the three relevant papers that are associated with this type of work, and we encourage you to take a look at this. This is largely motivated by increasing amount of distributed energy resources in the power grid. It is ranging from very, very low towards a level that will affect voltage, protection, and potentially be to the level that is as big as traditional large-scale bulk level generation resources. And during this process, artificial intelligence is going to play a very important role in studying the issues associated with their impact on voltage control and on protection. And that's exactly what we are going to talk about today. Let's first start with the voltage regulation problem. This is referring to the distribution systems where you have rather limited amount of control capabilities with a lot more nodes or buses, and the possible actions that the utility companies can perform today are really through either discrete level switching or continuous control, such as photovoltaic inverters. The goal is, of course, to minimize the voltage deviation with respect to resource constraints. And one could use a simulator such as OpenDSS to validate the performances before they deploy them into the real world. There has been a lot of work in these directions, including some non-reinforcement learning based approaches, and some are communication free, some are with limited amount of communication. And some of the key challenges in this type of work is that how could we try to minimize the assumptions with regard to the system model and parameter, given the legacy distribution systems that has rather limited visibility? And how do we make that control decision flexible to the best that we can in changing operating conditions? And how do we make the control policy as automatic as possible? So in this particular piece of work, we frame it as a Markov decision process and utilize reinforcement learning to solve it. Reinforcement learning is a very active field of study. It is continuously observing the state of the system and trained it over a predefined reward function. And the action is continuously being updated as a goal of maximizing the reward function that we gave to the system. So there has been a number of work along those lines. And one of the unique aspects that we are doing here is to utilize the photovoltaic generation to provide both real power and reactive power in view of minimizing the voltage violation and within the resource constraints. And it is totally a model-free approach. And we study this problem because in most of the distribution systems are rather unbalanced across the three phases. So this reinforcement learning framework is naturally fitting to this setup. And we do not need to know much about system parameters. And we can design a reward signals which would reflect meaningful and desirable system behavior rather than a certain functional restrictions. And we can employ off-the-shelf state-of-the-art reinforcement learning tools that has been shown to be very successful in other domains of applications. So this is the way we model them as a MDP problem. The reward here is worth noting is to regulate the voltage within the band and maximize the utilization of the photovoltaic power generation. And the action space here is the way we control the real and reactive power. And the parallel neural network is trained, and agent would adapt to one another for system-wide objective. We use the proximal policy optimization. Each iteration corresponds to about 10,000 timestamps, and decentralized agent trains more monotonically and with less variance in the episodic rewards. So this is something that is worth noting, which is we can show that as a result of this objective function, we are jointly optimizing the provision of both real and reactive power from the photovoltaics. In other words, it is somewhat counterintuitive that the photovoltaic solar panels are not always producing at their maximum amount of real power, but rather at certain period, they might instead purposefully reduce a small amount of real power injection in exchange for their capability to provide some reactive power VAR support in view of the voltage potential violation. And that is implemented also through the OpenDSS simulation into this Open Grid GEM simulator that we have developed. So that's one piece of work, which is utilizing reinforcement learning for voltage regulation in DER-rich distribution systems. Moving forward, I would like to talk about another application, which is also in the context of deep distributed energy resource penetration systems, and the protection problem is of the interest in this paper. As many of you may or may not be aware, protection is really the safeguard of the power grid. It protects the grid by isolating faulty segments. And as an industry, it is a very expensive industry with $100 billion plus dollar asset in the whole industry. So with the growing amount of fluctuation in the net load, protection becomes a major challenge. The challenge can be summarized in this conceptual example. Traditionally, a fault is detected by examining the current that is going through the reclosers. However, if the DERs are very close to the fault situation, there might be a situation where the photovoltaic generation is trying to pull up the voltage in between, which then reduces the difference between the normal operating condition and faulty operating condition. And that is going to make the recloser somewhat confused. They don't have a good, clear boundary to classify a normal versus abnormal situations. And that is a challenge for today's design of protective relay. There are further challenges that if there were more than one closer, then coordination becomes also a challenge. The coordination between the fuse and recloser in this example during the fault would be of a big challenge when you're seeing a photovoltaic generation in the upper side of the fuse. And if there are such a fault, then they might have accidentally first disabled the fuse operating before the recloser, which is a coordination error. With that said, there could be major opportunities from the machine learning community to modernize the design of the tripping action of the protections. Essentially, you can think of today's protective relay as a single or two-dimensional decision process, looking only at certain measurements of current or voltage. However, as we articulated in the previous couple of examples, there needs to have a much higher dimension of features in order to make a proper decision for such relay decisions. And that is very nicely suited in a machine learning context of finding out a region of action space in a high dimensional featured space. So it is very promising to explore the potential of using machine learning based design in the protective relay setup. So we modeled the relay of a distribution systems as a multi-agent reinforcement learning problem. Here, the key decision is embedded in this blue dotted box, where there is a deep neural network trying to be trained and optimize the designed reward function. There is a state that includes voltage, current, breaker state, and counter. And the action here is continue or reset or set counter. So this is the way that is designing potentially needed coordination actions across multiple relays in a distribution systems. And the reward function is also designed according to the domain knowledge that we have. In general, solving a multi-agent reinforcement learning problem is very difficult. However, here we are taking advantage of the radial structure of the distribution systems, and then utilize a nested reinforcement learning approach to make the most out of this structure, by which we mean that you first train the relays based on the operation dependency. In other words, you always start the training from the very end. When you're doing the training from the very end, it does not really matter what's the status of the upstream relays. So in other words, the training can be done in a nested way, starting from the most local information and then extending to the next layer and next layer. That way, you can significantly reduce the need and burden on computation. And that's the proposition that this can be trained sequentially using a single agent learning method. And in a distribution grid that is totally radial, this proposed RL protection is a nested problem and can be executed without any communication needs. And this is the experiment design. It is also open sourced. And here we would like to show the performance of the conventional relay versus the proposed relay when you increase the penetration of distributed energy resources. As you can see, the pre-fault and post-fault in the conventional relay, when the system becomes rather high penetrations, it can become quite erroneous. Whereas in the reinforcement learning based relay, the error can remain always very small. And this is the coordination issue that we discussed about. And in terms of the performance in this reinforcement learning based approach, you can see there is a rather reliable delay for the primary and backup protection. And we minimize the potential risk of miscoordination in this way of design. And with that, I would like to thank you for your attention. And then we would welcome your interest in looking more into reinforcement learning applications in the power systems. Thank you.